Okay, here we look at a theorem and a proof for the atoms of a Boolean algebra. And remember, the atoms are those non-zero elements of the Boolean algebra that satisfy the conditions that they are any element from the Boolean algebra. When you take A times U, you get back 0, or you get back A. And what we could say is they're the minimal building blocks of the Boolean algebra. They generate the rest of the entries. In another word you can use is they span the set. So let's look at, and that's for a finite Boolean algebra. Any finite Boolean algebra does have a basis, and those elements are called atoms in the basis, and they generate the rest of that finite Boolean algebra. So here, this theorem says a non-zero element A, we knew we needed non-zero, in a Boolean algebra B is an atom if and only if, for every pair of elements, we'll call them X and Y, in your Boolean algebra. Usually we use a script B to represent any Boolean algebra, so you don't confuse it with the B where you have zeros or ones, but we'll just call it B here. So take any elements X and Y in the Boolean algebra, and let's say that we add them, whatever the operation is for addition, you just want to add them. And if you are going to have that be the atom A, then the only way to add two elements from the Boolean algebra and get back an atom A is if A is equal to X, or the A is already equal to Y. Okay, what that means is this atom cannot be decomposed. I cannot write an atom as the sum of other elements in the set, other than having started with itself to begin with in one of those elements in the sum. Okay, so what do I mean? Let me go to my scratch paper. So I've copied down the theorem here. And remember the definition of atom. A is going to be non-zero, and then any element in the Boolean algebra, they call it U. If you take the product of A times U, you're going to get back the 0 element, or you're going to get back the A element. That's what it means to be an atom. So we can go back to our nice maybe B3, the 3-tuple space, where you just use the normal 0, 1 Boolean, multiplication, addition, and complement. So we remember how to do the Boolean algebra on that, meaning for the function of zeros and ones. Okay, so if I said, let's suppose that we have 1, 0, 0. So what I'm doing is I'm trying to just pick on any two at this moment elements from my set here, B to the third, the 3-tuple. So if I took maybe just these two, and I said, well, if I add those up, let's just see what happens when I add those up. If I add these up, so remember addition in this algebra is just or, so I say 1 or 1, just do it entry-wise, 1 or 1 is 1. Then I do 0 or 1. And then I do the next one. Then I do the next one, 0 or 0 is 0. Okay, so I end up with, and it is an element that's in the set, B to the third. But is this, so the question becomes, when I add these two X plus Y, so this is like my X, this is like my Y, can I call this an atom A? So the question is this an atom A? Yes or no? Well, it's not an atom. So remember, we already talked about what the atoms are. That is not a minimal building block, and we saw that in the Hasse diagram when we put a partial ordering on this. What you can do is you could even just look at the definition, and you'll see it doesn't hold. So if I said, suppose that I say, yeah, this is an A. If this is an atom, then if I take A and I'm going to use this one and this one's left-hand side, because if I do A times U, I should either get back 0 or A. So I'm going to take a U. Now I'm going to multiply though. If I take a U, so this is any element in the Boolean algebra. Well, I don't want to take 1 because I know I'm going to get back A if I use the 1 element. So that wouldn't be a good one to show you a counterexample. But let me take something else like 0, 1, 0. Notice what happens when I do the multiplication here. So this is an and now. So 1 and 0 is 0. Then do the next. 1 and 1 is 1. And then 0 and 0 is 0. Okay, so you can see that this is not matching up with the definition that's listed here for the atom, which we know this is what needs to happen. So if this is my A, and this is my some element that I picked out from B, so that's my U, did I get back 0 or the A? No, this is not the 0 element, which is 0, 0, 0, and this is not the A that I started with, in quotes, because it's not really an A. So this is not going to be an atom, so that cannot be an atom. And remember which one is an atom? So we looked at, let's erase this part here. Just 1, 0, 0 is an atom. So if I were to put, I'm going to put my atom over on this side, 1, 0, 0, I know that's an atom, minimal building block. Is there a way to add 2 elements from the Boolean algebra and get back the 1, 0, 0? Let's see. If you did 0, 0, 0 or 1, 0, 0, that would give it back to you. Or if you did 1, 0, 0 or 1, 0, 0, that would give you back 1, 0, 0. If you look at that component-wise again. So what do you notice about this? So this is an atom, but as the theorem states, for every x and y that you were to pick, if you are to add up those 2 values to get back your atom, so this is my atom. I've just written the A on the right-hand side now. So this is my atom on the right-hand side. What do you notice about the x and the y? Well, either the x has to be equal to the A or the y has to be equal to the A. So on this side, is the x equal to the A? Well, I'll just call this one x. Yeah, x is equal to A. So this is A, this is x, this is y, and that's A. Or what was the other thing? A has to equal y. So here's my A on this side. We will call, doesn't matter, this x. We'll call this y. So notice y is equal to A. Now let's look at the proof. So we're actually going to do the proof now. So going back, what do we have to prove? So we first have to show that for every element, we'll call it U, in the Boolean algebra, any element you take, if you start with the fact that A times U is equal to 0 or A times U is equal to A, that's just the definition of an atom, and again, A not equal to 0, it said a non-zero element A up here, then what should that imply? That needs to imply that for any 2 elements in the Boolean algebra that we pick up, called x and y, if we take their sum, x plus y, and set it equal to our atom, then the only way that this is going to occur is if A is equal to x or A is equal to y. So what we can do is assume that A is an atom such that A times U is equal to U or A times U is equal to A. So I've just picked on that assumption part here for all elements in B that you multiply the atom with, and let x and y be 2 elements that you take out of B and add them up. Okay, so you're going to add them up and set it equal to the value of your atom. Then what do you get? Okay, well then if I took A times X, I'm going to replace my A with that sum that I said. Let's just go ahead and set A equal to X plus Y. Let's assume we can just write A equal to X plus Y. So I'm going to take A and replace it with X plus Y. Then I'm still multiplying by X. So I'm going to distribute to get X multiplied by X plus Y multiplied by X. And then this ends up to give us, well, X and X is just X. And then I just used the commutative property of multiplication to write that as X times Y. Then you can use the distributive property, factor out the X, and you get X times 1 plus Y. Well, what do you know about 1 plus Y? Well, the domination rule there says 1 plus Y is going to be 1. And then what do you get for X times 1? Well, X times 1, the identity is going to give you back X. So far, you have this equation. Okay, so now we have A times X is equal to X. But remember in our assumption, we said A times X is going to equal to 0, or A times X is going to equal to A. So what does that mean for our right-hand side X? That means that X has to be 0, or X has to be A. So now if you suppose that X is 0, it has to be one of those. And where is the X coming from? It was in this relationship. We assumed that we were adding X to Y to set it equal to an atom. So suppose that the X is equal to 0. Then we would have Y equal to A. Isn't that right? So if we said, well, let's suppose that X is equal to 0, then we would have A is equal to the 0 element plus Y, and then by the property of the 0 element, 0 plus Y is just Y. So A is equal to Y, or you can say Y is equal to A. So that proves that for any two elements X and Y in your Boolean algebra, if you were to add them up and set it equal to an atom, then either the atom is equal to the X value, or the atom is already equal to the Y value. That means the Y is equal to the atom, or the X is equal to the atom. So we're not able to decompose an atom into the sum of two values, elements of the Boolean algebra, unless one of those is already the atom itself. So now what do we have to show? Now this was an if and only if proof. So now we show that for every two elements X and Y in the Boolean algebra, if we have A equal to X plus Y, means that A is equal to X or A is equal to Y, so we're going to assume that's true. Then this should imply that for every element in the Boolean algebra, so just one element we're going to call U here, we're going to have that the multiplication of A times U is going to give you back 0, or the multiplication of A times U is equal to A. In other words, it's going to imply it's an atom, and this is A not equal to 0. Okay, let's have U start in the Boolean algebra B, and assume that the A is such that this does hold, our assumption. If you take A and set it equal to X plus Y, then either the X is equal to A or the Y is equal to A. Then what do I know? Now I've worked it this way, but it might be more natural to work it on the bottom going up. So what I mean is you could start with A and say, well, what do I know A is? A is the same thing as A times 1, and that's the same thing as A times, you just use properties of Boolean algebras, the element plus U complement, and then from there you could say, well, I know I can distributive property, A times U plus A times U complement, and then what you have here is you have, let me just now write the right hand side first. Okay, so this implies that that right-hand side is equal to the left-hand side, which is A. So what do we have? So if this is equal to A, that means either A times U is equal to A, or A times U complement is equal to A. So that's this statement right here. So let us suppose that A times U complement is equal to A. So if we do have A times U complement equal to A, then what do I know about A times U? So why are we picking on A times U? The reason we're picking on A times U is because that is in our conclusion statement here. I need to verify that A times U is 0 or A times U is A. So let's see what A times U is. So I have A times U. Now I'm going to replace this A with what I'm supposing. I'm supposing that A is equal to A times U complement, because we already know that we said A times U could be A. So that takes care of that statement. So we're halfway there. But now how do I get this 0? A times U is equal to 0. Well, if I suppose that A is equal to A times U complement, then I replace that A times U complement for A. Then I multiply by U. I can use the associative property for multiplication and group these two values at the end. And what is U complement times U? In any Boolean algebra, and U is coming from a Boolean algebra, it's going to be the 0 element. So we've written the 0 element here. And then what is A times the 0 element? Well, A times the 0 element in any Boolean algebra is going to be the 0 element. And again, I put the 0 in quotes because it's whatever that 0 element is for that Boolean algebra. So what did we get back? So that means that A multiplied with U will give us back the 0 element in this case. But before, we also said that A multiplied by U could be A. So that's the OR statement. So A multiplied by U is equal to the 0 element, or A multiplied by U is equal to the A element. And that is all that we needed to prove for this last part of the theorem.